One of the lesser discussed logistical realities is not found in battlefield maneuvers or diplomatic negotiations, but, in the quiet failure of materials under stress. Timber, widely used in field fortifications, temporary bridges and supply structures, often degraded far faster than planners anticipated. Cold winters, humid summers, and repeated freeze-thaw cycles exposed a vulnerability in modern construction practices. Wood that had not been properly conditioned or protected did not simply age, it collapsed unpredictably under environmental strain. This was not an isolated engineering issue. It reflected a broader assumption that industrial production could replace environmental adaptation. One of the most important preservation agents used in medieval Europe was tar, produced through the controlled burning of pine wood in low oxygen conditions. This substance was not applied superficially. It was worked into the grain of timber, allowing it to penetrate deeply into the outer layers. The function of tar was not to seal wood in an impermeable layer. Instead, it modified moisture exchange and inhibited biological growth. By reducing permeability while retaining flexibility, tar allowed wood to respond to environmental changes without structural failure. This balance was essential in climates where humidity and temperature fluctuated significantly. Other treatments complemented this approach. Oils derived from animal fats or plant sources were used to condition fibers and slow moisture absorption. In some regions, lime-based coatings provided an alkaline surface hostile to microbial growth. These were not isolated techniques but part of a broader system of material conditioning that addressed multiple forms of degradation simultaneously. Structural design reinforced preservation by controlling environmental exposure at the architectural level. Material treatment alone was not sufficient. Medieval builders integrated preservation logic directly into construction design. Roofs were extended to direct water away from vertical surfaces. Foundations were elevated or constructed using stone to prevent direct soil contact, which is one of the primary pathways for moisture-related decay. Water management played a crucial role. Drainage systems, even in simple settlements, reduced prolonged exposure to standing water. Buildings were often positioned with consideration for natural water flow, avoiding low-lying areas where moisture accumulation would accelerate degradation. Joinery techniques also contributed to longevity. Traditional joints such as mortise and tenon allowed for slight movement without structural failure. This flexibility was not incidental. It prevented rigid stress points that would otherwise crack under seasonal expansion and contraction. In effect, the structure was designed to move without breaking. Maintenance was not an afterthought, but, an integral part of the system. Unlike modern construction models that often assume minimal intervention after completion, medieval timber structures were designed with ongoing maintenance in mind. Individual components could be replaced without dismantling entire buildings. This modularity extended functional lifespan significantly. Regular inspection and repair cycles ensured that early signs of decay were addressed before they spread. This required a level of material familiarity among builders and occupants alike. Knowledge of how wood behaves over time was not specialized. It was practical, widespread, and really embedded in construction culture. This maintenance-oriented mindset reflects a different relationship with durability. Longevity was not achieved through permanence, but through adaptability. Structures survived because they could be continuously adjusted to changing conditions. When compared to modern military logistics, these methods reveal contrasting assumptions about material reliability. During 20th century conflicts such as the Korean War, rapid construction and deployment often prioritized speed over long-term conditioning of materials. Timber used in temporary fortifications and support structures was frequently processed under time constraints that limited seasoning and environmental adaptation. In environments characterized by extreme temperature variation and high humidity, this created predictable challenges. Wood that had not fully stabilized responded poorly to environmental stress, requiring frequent maintenance and replacement. While modern logistics compensated for this through supply chains, the underlying vulnerability remained. The contrast is not about technological advancement versus historical simplicity. It is about differing constraints. Medieval builders optimized for longevity under scarcity. Modern systems often optimize for speed under abundance. Each approach reflects its operational context. The underlying principle is that durability emerges from system integration, not isolated techniques. The longevity of medieval timber was not the result of a single secret method. It was the product of a coherent system that aligned material selection, environmental control, chemical treatment, structural design, and maintenance practices. Each component reinforced the others. This systems-based approach remains relevant because it reflects fundamental material behavior. Wood does not exist independently of its environment. It responds continuously to moisture, temperature, biological activity, and mechanical stress. Effective preservation requires engaging with all of these factors simultaneously. Modern materials science has expanded the tools available for addressing decay, but the underlying challenge remains unchanged. Durability is not simply engineered into a material, it is sustained through ongoing interaction with conditions of use. What medieval practices ultimately reveal is a philosophy of working with material limits rather than attempting to eliminate them. The so-called anti-rot secret was not a hidden formula, but a disciplined approach to observation and process. Medieval builders did not attempt to stop decay entirely. They managed it, delayed it, and designed around it. This distinction is critical. It reflects a practical understanding that all organic materials exist within cycles of change. In survival contexts, construction planning, and even historical analysis, this perspective remains valuable. It shifts focus from short-term performance to long-term behavior. It encourages attention to process rather than outcome alone. Understanding these systems is not about replicating medieval techniques exactly. It is about recognizing the principles that made them effective and considering how those principles apply under different conditions. These are not forgotten tricks of construction. They are structured responses to a material reality that has not fundamentally changed. If you find value in exploring these deeper historical systems and their practical implications, subscribe to History Vault and, share this video